Hello, all of you. Today we are going to discuss the new topic, that is reduction by lithium aluminium hydride, that is LiAH4. Okay. In lithium aluminium hydride, this is the you can see here. This is the structure of lithium aluminium hydride, where there is a ionic bond between lithium and aluminium. You can see it here. Uh, First, we will see the applications of lithium aluminum hydride. As lithium aluminum hydride is a powerful reducing agent which reduces many functional groups to the corresponding product. It can reduce aldehyde to primary alcohol, ketone to secondary alcohol, esters to primary alcohol, carboxylic acid are converted to primary alcohol, amide is converted to amine with this lithium, this lithium aluminum hydride. After that, cyanide is also reduced to amine. C triple bond N is reduced to CH2NH2. Then NO2 group is reduced to NH2. Epoxide ring opening reaction takes place, reduction, and via this lithium aluminum hydride, uh, the halide reduction also takes place. So first we will discuss the applications, and later on we will see the mechanism of every conversion, how it takes place, what is the path of the reaction, that we will see later on. Okay. Okay. So here is okay. So see here, this is aldehyde. Here aldehyde functional group is there. It is reduced to primary alcohol. It is reduction. This is ketone. Ketone is reduced to secondary alcohol. This is carboxylic acid group, and that carboxylic acid group is reduced to CH2H. Yeah, as I told you, ester is also reduced to CH2H, like primary alcohol. Amide group, CONH2. Amide is reduced to CH2NH2, that is amine. It is C triple bond and cyanide. Cyanide is also reduced to CH2NH2. This is epoxide ring. Epoxide ring opening reaction takes place, and we get the secondary alcohol. Ring is open. Now ring opening, whether from this bottom side or upper side, it depends upon the substitution. If as it is equally substituted epoxide ring, there is no question of ring opening. Ring may be open from this side, or it may be open from this side. Okay, this is lactone, cyclic esters. Ester group cyclic esters are called as lactones. Lactone ring opening reaction takes place where this bond pH takes place and reduction takes place, and we get this carbonyl group as usual will reduce to alcohol, primary alcohol, and this oxygen, this inside OH will form, and we get this isolated diol. where opening reaction takes place. This cleavage of carbon oxygen, carbon in carbon and oxygen takes place. We will be separated. Yeah, it is important. Acid chloride, C double bond OCl is also reduced to primary alcohol. NO2, NO2 is also reduced to NH2. Okay. Now see here, these are the important examples where this is the carbonyl group and this is a carbon-carbon double bond. They are conjugated to each other, double, single, double bond. This is the carbonyl group and this is a carbon-carbon triple bond. It is a non-isolated. This is sorry, it is isolated. This is non-isolated. So here in this example, you can see there is alternate double single bond, double single double. It is a conjugated ketone. It's called as enone. And here it is not conjugated, it is a non-conjugated. So what is the beauty of this reagent? That it doesn't reduce the carbon-carbon double bond or triple bond. It reduces only carbonyl group, cyanide group, amide, nitro, and halogen atom. Such all the reduction, almost all the functional groups are get reduced by this reagent, but not carbon-carbon double bond or carbon-carbon triple bond. Why it is so? Why the carbon-carbon double bond or carbon-carbon triple bond is not reduced? Because carbon-carbon double bond have the pi bond, so there is the pi electrons, and hydride ion, the lithium aluminum hydride is hydride ion donor. So that hydride ion cannot reach to, means there is a repulsion between pi cloud of the carbon-carbon double bond or triple bond and the hydride ion because both are electron rich. Hydride ion is electron rich as well as pi bond from the multiple bond, that is double or triple bond is also electron rich. So repulsion takes place. Hydride ion cannot reach to that carbon-carbon double bond or triple bond. But when in case of carbonyl group C double bond O or C triple bond L, what happens? There is a polarity. In C double bond O, pi bonded electrons are always shifted on the oxygen, so oxygen bears the negative charge. Carbon has the positive charge deficiency there. Means although there is a pi bond, but it is a polar, so it is shifted more towards the oxygen. Same is the case in cyanide also. You see triple bond N, carbon is deficient and nitrogen has the negative charge. So there is also polarity. In that case, hydride ion can reach there to the multiple bond, that's pi bond, and reduction takes place. But in case of carbon-carbon double bond or triple bond, that type of reduction is not possible. Okay, so this example self-explanatory that there is a no reduction of carbon-carbon double bond or carbon-carbon triple bond takes place. Only there is a reduction of carbonyl group to secondary alcohol because it is ketone. In both the case you can see secondary alcohol is converted to ketone. Okay. See, this is the example again, same type of example. It is carbonyl group. That carbonyl group is converted to secondary alcohol. This is carbon-carbon double bond. That carbon-carbon double bond is remains as it is, not no reduction. There is a carbonyl group, which is reduced to secondary alcohol. And carbon double bond remains as it is. This is again example that carbonyl group is reduced to secondary alcohol, and this carbon-carbon double bond is remains. Okay. Yes, this is important. Now let us recall this example again. See, this carbon-carbon double bond is attached to the alkyl group. Alkyl groups are electron donor as per plus sign effect, inductive effect. So that that methyl group, that alkyl group donate the electron to this carbon. Usually there is electron rich, the carbon-carbon double bond is electron rich. And again, this methyl group is electron donating. That's why the electron richness is increases. Therefore, there is no question of hydride attack on that on this carbon-carbon double bond, no reduction. But here, What is the change here? Instead of lithium, there is a phenyl ring. Phenyl ring. It is a aromatic ring, and we know that it is an electron withdrawing group. High is electron donating, that's what plus I effect, and pencil ring is the electron withdrawing. And hence, if you don't have plus, it withdraws the electron from this center, and therefore the electron richness, you can say it, electron richness is decreased. You can say, compared to this carbon-carbon double bond, the carbon-carbon double bond which is attached to electron withdrawing group like phenyl ring or NO2 group, any electron withdrawing group is less electron rich. And therefore, hydride ion can reach there and the reduction takes place. Therefore, this carbon-carbon double bond is reduced to single bond. It means there is addition of hydrogen atom. Two hydrogens across carbon-carbon double bond takes place. There is no doubt carbonyl group is connected to secondary electron. That is the normal case. Now remember, that is the case. If electron donating group is there, then carbon-carbon double bond is not reduced. And if electron withdrawing group is there, then carbon-carbon double bond is also reduced. But when in both the cases, I am talking about the conjugated compound, orbital saturated ketones. Oh, now see this example again. Yes, this is repeated. Here it is aldehyde group, that aldehyde group, carbon-carbon double bond in conjugation. So both, that is aldehyde, is converted to primary alcohol, and this carbon-carbon double bond is reduced to carbon-carbon double bond. Because why it is so? Because phenyl group, that is electron withdrawing group, is attached to that side. Okay. But again, I want to tell you one thing about this. See here, the temperature is in all these reactions 35 degrees Celsius. Okay, so means more than, just a little bit more than. Okay, now here see the temperature effect. So this reaction, same reaction is same, but the reaction is carried out at low temperature, below 0 degree, minus 10 degrees Celsius approximately. So in that case, it is observed that this carbon-carbon bond is not reduced. It is remains as it is, even though there is an attachment of phenyl group. Why it is so? At low temperature. So remember, at 35 degrees Celsius, then phenyl group, electron withdrawing group is there. Then reduction takes place of carbon-carbon double bond. But at minus 10 degrees Celsius, one phenyl group, that is electron withdrawing group, is present. No reduction of carbon-carbon double bond takes place. However, in soon this carbonyl group will be converted to secondary alcohol. There is no question about it. See this one example. This is carbon-carbon double bond. When ring is there, and we expect that the carbon-carbon double bond will also reduce along with this aldehyde group, but it will not happen because the temperature is a low, less temperature, minus 10 degrees Celsius. So you can see in the product, carbon-carbon double bond is as it is, and with the secondary alcohol is converted to primary. Now let us see the mechanism of this reduction. That how aldehydes are reduced to primary alcohol and ketones are converted to secondary alcohol. Let us see the mechanism. Okay, see, this is LiNH4, as I told you. The ionic bond is there in between Li positive lithium ion and this aluminium ion. And aluminium is attached to 4 hydride ions, 4 hydrogen atoms, and they are released as a HNO2, that is hydride ion. Okay, see how it happens. We see with this lithium oxygen bond formation takes place, and after, because lone pair is there on the oxygen, lithium is electron deficient. Okay, so that what will happen? Then this 500 electrons, it is not shown here, but you can see this 500 electrons is shifted on oxygen, because oxygen is electron deficient, because the formation of lithium oxygen bond takes place. Oxygen is a divalent, it is the third bond between oxygen and lithium. So in the next step, what will happen? 500 electrons will open into oxygen. And this carbon will have the positive charge, which is deficient now. Therefore, in the next step, this aluminum hydride donates its hydride with this carbon ion. So C positive and H negative bond is formed. Okay. Now in the next step, you can see here the oxygen aluminum bond formation takes place. Now this is the alkoxy aluminum lithium aluminum hydride, where out of 4 hydride ions from the aluminum, 3 are filled there with aluminum and 1 hydride is transferred to the oxygen. Sorry, carbon and carbon. One molecule of lithium aluminum hydride can produce 4 molecules of ketone or aldehyde. So this is because again it has the 3 hydride ions, it will again in the same fashion react with 3 molecules of ketone, and we get tetra alkoxy lithium aluminum. So it happens step by step. So first we will get we have later this is the lithium alkoxy lithium aluminum hydride, then dialkoxy lithium aluminum hydride, then trialkoxy lithium aluminum hydride. Finally, we get tetra alkoxy lithium aluminum hydride, which on subsequent hydrolysis is converted into secondary hydride. It also starting material is ketone. And 4 molecules of secondary alcohols are obtained. This aluminum trihydroxide and lithium hydroxide are the byproduct of this reaction. If you start with the aldehyde, you will get the dichemical. Okay, let us see the mechanism of reduction of ester. Here, this is ester molecule, RC double bond R. This is lithium aluminum hydride. 5 bond is open on the oxygen in the same fashion. In the head that we have discussed in the previous slide, hydride ion transfer, we get this alkoxy lithium aluminum hydride, where 1 hydride from the aluminum is transferred to the carbon with carbon, which is electron deficient, and we get this molecule. But here the mechanism, subsequent mechanism is totally different. In that case, the step in the previous case of this of aldehyde and ketone, there is a transfer of hydride ion. Here, what happens? This negative charge, because oxygen is negative charge, this negative charge, that is just 2 electrons, are again returned back, and there is a removal of alkoxide ion. Yes, alkoxide ion, I can also say. So RO negative, because alkoxide ion, RO negative, is a good living group, and what we get this negative. C double bond H, that is aldehyde. The first step, remember, ester is first converted to aldehyde. Is it reduction? Yes, it is a reduction because there is a removal of oxygen. In ester, 2 oxygen atoms are there. In aldehyde, only 1 oxygen is there. Okay, so that is a reduction. Now, second molecule of lithium aluminum hydride is coming to play, and as I told you in the previous slide, the mechanism will be same. That aldehyde molecule will be converted to primary alcohol. You can write the mechanism. Just refer the previous slide. First monoalkoxy lithium aluminum hydride, then dialkoxy lithium aluminum hydride, then trialkoxy lithium aluminum hydride, and finally tetraalkoxy lithium aluminum hydride is will form tetraalkoxy lithium aluminum, not hydride, because all the hydrides will be done. Then we will get hydrolysis, first acid hydrolysis. We will get the 4 molecules of corresponding primary alcohol along with the formation of byproduct aluminum trihydroxide and lithium hydroxide. Okay, so what we have discussed so far up till now, we have discussed that the lithium aluminum hydride is a powerful reducing agent. It reduces aldehyd to primary alcohol, ketone to secondary alcohol, ester to primary alcohol, then nitro group to NH2, cyanide to CH2NH2, carboxylic acid to primary alcohol, that is CH2OH. Halide halogen atom is also reduced with X, chlorine, hydrogen, iodine, by H. Okay, that is the and cyclic ester, that is lactose, are also reduced to alcohol recluse. Epoxide is also very powerful reducer needed. After that, we have talked about the alpha-beta unsaturated ketones. In alpha-beta unsaturated ketones, if the carbon if the carbon-carbon double bond is attached to the alkyl group, that is electron donating group, in that case carbon-carbon double bond will not reduce. But if it is attached to the electron withdrawing group, that is, for example, phenyl cyanide or nitro, where it may be, then carbon-carbon double bond is also reduced due to the electron withdrawing nature of that group. Okay. Otherwise, carbon-carbon double bond and carbon-carbon triple bond are not reduced. Okay. Then we have discussed another aspect of this. All the reactions are discussed at 55 degrees Celsius, just more than the room temperature. But if you carry out the reaction at low temperature, below 0 degrees Celsius, approximately minus 10 degrees Celsius, in that case, carbon-carbon double bond. I'm talking about the alpha-beta unsaturated ketone. The carbon-carbon double bond of alpha-beta unsaturated ketone is not reduced. Whatever maybe the substituent, whether it is electron donating or electron withdrawing. So this is the for this lecture. We will see the remaining part of this lecture, and we will continue this lithium aluminum hydride in next lecture. Okay, so thank you.